Greetings, everyone. Welcome back to college algebra. Time for that third section to start. We begin with quadratic functions. You've already seen a lot of the information that goes along with this in several different scattered places. And this section is designed to just bring it all together and talk about this one type of function. A lot like we talked about lines at the beginning of the last unit, right? We just basically downloaded everything we could about lines. Okay, well, this is not much different, except now we're talking about quadratic functions which graph to parabolas. Okay, so with the parabolas, there's just a few different features that we have to pay attention to. First of all, though, let's start with the algebra side. Notice the function is, of course, a quadratic, something that x squared is the highest power, but I can also have an x term and a constant term. One form is to have it in that quadratic looking format. I call that general form. Another form is we can have what I call vertex form, where you have x minus some number, quantity squared, times some number, plus another number. Okay? And this should look familiar to you a little bit because this is the form that you would have seen one of these back in the translation section when we were graphing things via shifting and reflecting and stretching and things like that. This is the format that fits with that kind of process. But our quadratic functions can be in either format, and you need to be able to find all of the important pieces of information from both formats. Okay, so here I've got all of the different stuff. Let's go through the things that you'll need to have to find. Okay, one, the most important point on the parabola is the vertex. The vertex is the very bottom extreme point or the very top, depending on if your parabola is facing up or down. It's an extreme point. It's also the turning point, which is why it's so important to know where that point is, because it's always the most difficult to graph the piece of a graph. It's most difficult to draw that piece of a graph where the major turn is. So if you know exactly the point where it turns around at, then the graph is going to be pretty easy to draw. Okay? Also, any word problems that are typically used just with quadratics are problems that like to use that extreme point to their advantage, like maximizing profit or minimizing cost or maximizing usage of some distance or volume or whatever. It can be a minimum and it can be a maximum. It just depends on if your parabola is facing up or down. Now remember, the way we determine if the parabola is facing up or down is the number multiplied in front of the squared. Notice I have capital A here and here. That was not an accident, nor is it a coincidence. Those two numbers in both formats will be the same. Okay? If A, this number here, is positive, same as here, then your parabola will be facing up. And if A is negative, then your parabola will be facing down. Okay? If it's facing up, your vertex is a minimum. If it's facing down, your vertex is a maximum. Okay? So how do I find that vertex? Well, if you're in vertex form, hence the name, right, you can literally read it. It's the shifts, because the original x squared is centered at the origin. So if I shift left or right or up or down, whatever those shift numbers are, they're adding to 0, which means you get the same numbers back. So whatever these shifting numbers are in this format, that's going to give you the vertex, right? If it's a left or right shift, that'll give you the h. If it's an up and down shift, it'll give you the k. And that's going to be your extreme point, the vertex. In general form, though, we don't have that ability to just read it off. Instead, we have the connection between the two formats. And the connection is that if I complete the square on this quadratic, I'll actually end up in this format. That's actually how you convert between the two. You complete the square on the general form to get into vertex form. Vice versa, if you just multiply out the vertex form, write the parentheses and FOIL it out and whatnot, you go back from vertex to general. So that's the connection between the two. If I complete the square here, well, remember, completing the square, I would first have to factor out the a, which would make b divide by a. And then I would have to take half of the middle and square it in order to make the completing the square process work, right? So what we would end up with is negative b divided by 2a is actually in that position where h is. Okay, well, technically plus, but then, you have to do the opposite when you're solving for something. Okay, long story short, if you're in general form, you perform the calculation negative b divided by 2 times a, and that will give you the x component of the vertex. Then you just have to remember that k is a y value, and it's the y value that goes with h, and you have a function. Remember, what happens when you feed a function an x value is it gives you a y value, right? So if I plug h into the function, the calculation that I get out from that will be k. So then I have a way of calculating here, you see, the vertex if I'm in general form. Okay, so either way, you need to be able to find the vertex, either reading it or calculating it. All right, and we'll get some examples of that in a moment. The axis of symmetry is the invisible line that acts as the halfway divider of this thing. If you cut this parabola in half, the two sides are symmetric around it. They're mirror images of each other, half and half. The axis of symmetry always goes through the vertex, and it always points in the direction that the parabola is opening. Technically, it's pointing in the other direction too, but what I mean is it's not a line going like this or horizontal or whatever. Since we're only doing parabolas that open up and open down, all of our axis of symmetries will be vertical lines. Think back, vertical lines always have what kind of equation? X equals a number. That was back from the last unit. Well, it goes through the vertex. So when I put x equals h on these, I'm not just saying what the x value is. That's actually the equation of this vertical line. When you're asked to give the axis of symmetry, you are going to need to give the equation. Don't make the mistake. I've seen it a bunch. Don't do it. Don't give just h. A line is not just a number. The line needs an equation. So give x equals and then whatever the h value is. And that's the equation of your axis of symmetry. All right? Of course, you'll also need to find x and y intercepts. The y-intercept in general form, by the way, is quite simple because x is 0, so these pieces zero out, and you're just left with the c value. In vertex form, you'll have to calculate, plug in 0 for x, and then compute the rest out. In either format, here's a little trick for x-intercepts, not necessarily to help you find them because that is what it is. For x-intercepts, you're going to be plugging 0 in for y. So notice right here, you'd just be solving a quadratic equation. Over here, you would still be solving a quote-unquote quadratic equation, but it'll be more like moving things around. Okay? So then here, here's a little trick, though, that might save you time every once in a while. Notice that if A and K are opposites, in other words, A is facing up, but K is moving down, or A is facing down and K is moving up, you'll have two x-intercepts either way. If A and K are opposite in sign, the number parts I'm not talking about, just the SIGN on A and K. Literally the number in front and the vertex shift, like up or down, right? If K is 0, no matter what, if K is 0, that means it's on the x-axis. That means the vertex is your x-intercept, and you don't need to search any further. And in the case where A and K are the same sign, that means A is positive, facing up, and K is shifting up. Well, here's your axis. I'm facing up and moving up. I'm moving away from the axis. Or if A is negative and K is negative, I'm facing down, moving down. Again, I'm moving away from the axis. Notice either one of those cases where a and k is the same, both positive or both negative, I have no x-intercepts. Okay? Now, if you forget this particular bit of information, that's okay. When you go and solve your intercepts, you might get imaginary values, right? Because it's a quadratic. You could square root a negative number. That's what will happen in this case. If you get imaginary numbers, it just means that you have no intercepts. Okay? So, big recap here. When you have a quadratic function, you need to be able to find the vertex. You need to be able to give the equation of the axis of symmetry. You'll need to give the domain and the range of these guys, which, let's comment on that for a second. Notice the domain never changes here. These are polynomials. So the domain's always the entire number line. But the range will be different depending on whether it's facing up or down. If it's facing up, then the range is going to be from k to infinity. Notice the bracket on the k because it's the minimum value here. The y value there, the lowest y value will be k. And here, the k value is the top, right? So the range on this guy is going to be negative infinity to k. Okay? So, recap. When you're given one of these functions, you have to be able to find the vertex. You have to be able to give the equation of the axis of symmetry. You need to give the domain and range. You'll have to comment on the intercepts. What is the y-intercept? How many x-intercepts and what are they? And then lastly, you'll have to draw a semi-decent graph. Okay? That's basically what these kind of problems are going to boil down to. And then we have a few other examples of a few other problems that I'm going to work as well. Let's get in some examples on analyzing these types of functions here. Let's start with these two guys. First, I have f of x equals negative 2 times x minus 4 quantity squared minus 1. And that should look a little bit familiar from the translation section. We can tell right away that it's a parabola, right, because of the x squared. It is facing down. It's been moved 4 to the right, and it's been moved 1 down. Okay, so let's analyze all of that. Let's write all that down. Alrighty, so we can see right here that it's facing down. Shift down and to the right. So my vertex is 4, negative 1. All right. And my axis of symmetry is x equals 4. Remember, it's the equation, x equals 4. My domain and my range. Of course, as always, the domain is going to be all reals, right? You can use the double line R for that one if you want. And the range is going to be, since it's facing down, I'm going to go from negative infinity up to the vertex being a max point, right? When it's facing down, the vertex is a maximum point up to negative 1 with a bracket. All right. So next, let's do our intercepts, and then let's graph it. Y-intercept, that's when x is 0. So f of 0 is equal to negative 2 times 0 minus 4 squared minus 1. F of 0, let's see, I've got negative 4 squared is 16 times negative 2. So f of 0 is negative 32 minus 1 is negative 33. All right? So I've got my y-intercept. What about x-intercept? Well, I happen to notice that there's going to be none, right? How did I notice that? Well, my A is negative and my K is negative, right? I can see A is negative and K is negative. That means it's facing down and shifted down. Also, another hint, look at the range. The range doesn't include any positive numbers. It's all negative. The Y values never cross over the x-axis. So there are no x-intercepts. What if you didn't remember to look for that? Remember we said it's okay. If you solve this equation, 0 equals negative 2x minus 4 squared minus 1. Real quick, I'll add the 1, divide by negative 2. And then I'll have to take a square root. But notice I'm going to be doing the square root of a negative number here, which is imaginary. Okay, so you can save yourself some solving time if you just notice that if the A and the K are the same sign, that you're not going to have any x-intercepts. So then let's draw a quick version of the graph here. I'll put some axes down. Let's see, my vertex is at 4, negative 1. So that would be right here. My y-intercept is probably too far down to graph. 0, negative 33. So my y-intercept is somewhere like, way almost off the board maybe. If you're still not sure about drawing the graph more precisely here, I know that it's facing down, right? So I know I'm going to be doing this. It may help if you plug in some more points. Sometimes that can help too. So for example, I could say what is f of, and since the vertex is at 4, it's probably a good idea to pick points that are right around that. So maybe I'll figure out what f of 3 is and what f of 5 is, since those are on either side. But again, it's a symmetric shape, right? Since those are 1 on each side, these two output values should be the same. If they're not, then you might want to double check. So f of 3, 3 minus 4 is negative 1, squared is 1. I'll get negative 2 minus 1, negative 3. 5 minus 4 is 1, squared is 1, times negative 2 is negative 2, minus 1 is negative 3. So if I plug those in and get that extra bit of information, that can help too. So 2, 3, and that's at these 2 points, so that would be here and here, right? Okay, so in this case, that's pretty decent to draw. The parabola like this, right? And I know it's not much better than what we were doing in the translation section, but you got to remember that accompanying this graph here is all of this other information that we found. We're not just going to hand over a graph. We would be handing over all of this other analysis that we've been doing. Okay? Next, g of x equals x squared plus 6x plus 9. Well, I notice that I'm in standard form, right, or general form, and I'm noticing that there's a positive 1 here in front of this. So I know that my parabola is facing upward because that's a positive number for my a value. Okay? Next, I'm going to compute my vertex, but I'm in general form, remember, so my vertex, I'm going to start by doing the h calculation first, which is going to be negative, the b value here is 6, divided by 2 times a, which is 1. So this gives me negative 3 for my h value. So far what this is telling me is that my vertex is the point where negative 3 is the x value. That's what h is. Now remember, the other part of that calculation, k, is that I do the function with the h value plugged in. So in this case, that would be g of negative 3. So that's going to be negative 3 squared plus 6 times negative 3 plus 9. So I have 9 minus 18 plus 9. I'm getting that k is 0. So I've got that. My vertex is the point -3, 0. All right, so I've done that calculation. From there, let's list out the rest of the information. Axis of symmetry, right? That's going to be x is equal to -3, right? That's the equation for my axis of symmetry. My domain and range, of course, domain is still the same thing. I'll use interval this time, -infinity to infinity. And my range is going to be something that's facing up. So I start at my k value of 0 and I go up to infinity. And then let's talk about intercepts, right? My y-intercept, in this case, is a quick plug-in, right? G of 0 is 9. Right? In general form, right? Just plug in 0, and 0 plus 0 plus 9 is 9. What about x-intercept here? I don't need to do any calculations for x-intercept on this one either, and that's because I got another special case. Do you notice the y is 0? Don't forget, the x-intercept occurs when y is 0. And normally what I would do in that case is I would solve this equation. 0 is equal to x squared plus 6x plus 9. But I don't need to because I've already found the special case. The vertex has a k of 0. So my x-intercept is also my vertex. And in this case, I only have one x-intercept. Last time we had none. This time we have one. What's happening is the parabola is bouncing on the x-axis here. Okay, so let's graph it. Let's see. I need a little bit less on that side. Let's do 3, 4, 5 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. My vertex is -3, 0, which is right here. My y-intercept was 0, 9, which is right here. I could plug in a couple of other points since I don't seem to have much going for me here. -3 is my x value of the center here. So let's do g of -4 and g of -2. Those will be on either side of my center here, right? -2 and -4. So they should be the same output because I'm doing symmetric around the center here. The center, right, is x equals -3. So g of -4 is going to be 16 minus 24 plus 9, which is going to give me 1. And then g of -2 is 4 minus 12 plus 9, which is also 1. All right. So then I'm hitting this point here and this point here. They're up by 1 right there. So then I'm just going to draw my shape as best as I can. Like that. Okay? So this is the kind of analysis that you're going to need to do on one of these functions. Okay, let's see what we can pull up on here. We've got the first function, -2x minus 4 quantity squared minus 1. And it's of course the parabola that we were talking about there. Notice the vertex is at 4, -1. And we have points at 3, -3 and 5, -3. And as promised, the intercept, let's get to that one. Right here, as you can see, goes through at 32. well, negative. Negative, oh, 33, I mean. Negative 33. Okay, then let's space this thing back out. The other function was x squared plus 6x plus 9. Notice I have the vertex at negative 3 dead on the x-axis there. So it just has the one x-intercept. And it goes through the negative 4, 1 and the negative 2, 1 points. And it does actually have the y-intercept of 9. Let's get one more example of doing the whole analysis on a quadratic function. F of x equals 1/2 x squared minus 6x plus 9. Alrighty, so then from here, what I'm going to do is, like before, I'm going to find the vertex first. And I'm going to write down which direction it's opening, right? I can tell right away that since this is positive right here, that the parabola is going to open upwards. And I can calculate my vertex by computing h and k. H is going to be negative b, which is negative 6, over 2 times a, which is 1/2. And then from here, I can just simplify. 2 times 1/2 is 1, and double negative is positive. And so I'm getting 6 over 1, which is 6. Then my k is going to be whatever f of that 6 is. So I'll plug in 1/2 36 because it's 6 squared, minus 6 times 6, which is again 36, and plus 9. So 1/2 of 36 is going to be 18, which would then make negative 18 with the negative 36, plus 9 would equal negative 9. So then my vertex is the point 6, negative 9. Alrighty. Next, let's calculate, well, I can get a lot of the other important info from here, right? My domain and range and axis of symmetry, right? My axis of symmetry is going to be x is equal to 6. My domain, as usual, all real numbers. My range, I notice that I'm facing upward, so I'm going to start at the bottom. The vertex is going to be a minimum. All right, so then here, negative 9 with a bracket up to infinity would be my range. And let's calculate the x and y intercepts. Alrighty, the y-intercept is pretty straightforward. That's just going to be f of 0. And of course, this is 0, that's 0. I'm just going to be left with 9. So I've got my y-intercept now. And I've got all of these pieces of information. And I've got my vertex. Alrighty, so what's left is x-intercept and graph. So x-intercept is going to have to be where y is equal to 0. And that means I'm solving this equation. 0 equals 1/2 x squared minus 6x plus 9. I'm going to make this a little bit easier on myself by multiplying everything here by 2. So I'm going to do times 2 to the whole equation. And yeah, I know the parentheses around the whole thing is a little bit lazy on my part. Mathematicians are lazy. We're always finding shortcuts. So 2 times 1/2, of course, is 1. That gets rid of the fraction. 2 times negative 6 is negative 12. And 2 times 9 is 18. All right. From here, I'm going to notice that there are not two numbers that add to negative 12 that multiply to 18. Because there's only a few that multiply to 18, 3 and 6, 2 and 9, and 1 and 18, right? None of those are going to add to 12. So my answers are a little bit more interesting than just the normal whole numbers. I'm going to have to use the quadratic formula to find them. Okay, so let's do that. Let's see. X is going to be equal to negative b, and in this case my b is negative 12, right? Because I changed it. Plus or minus square root. Negative 12 squared is 144. Minus 4 times 1, 4, times c, 4 times 18, all over 2a. 2 times 1 is 2. Okie dokie. So then x is going to be equal to 12 plus or minus the square root of 144 minus 72. That's ironic, right? 72 happens to be half of 144. Yeah, because of the 4 and the 9 that are square numbers there. Over 2. So then what I have here is 12 plus or minus the square root of 72 over 2. I can reduce the square root of 72, right? Because the square root of 72 is the square root of 36 times the square root of 2, because 72 is 36 times 2. So that's going to be 6 square root of 2. Alrighty. So I have 12 plus or minus 6 square root of 2 over 2, which means I have 3 plus or minus, or not 3, 6 plus or minus 3 square root of 2. These are my x-intercepts. Okay? Let's actually crunch those up though, because I need to get them on a graph. So let's see. 6 plus 3 square root of 2. I've got 10.2 approximately. So my x-intercept is going to be f of 10.2 is approximately 0. And the other one is 6 minus 3 square root of 2, 1.757, so 1.8-ish, right? So there are my x-intercepts at 10.2 and 1.8. So now the only thing left is to draw the graph. Okay? So let's see. Let me just get a couple of straight lines here. Make it a little bit easier on myself. Okie dokie. Put some marks on here for me. Same thing here. All right. So I've got 15 in each direction. Okay. So let's graph our important points first, right? The y-intercept, f of 0 equals 9. So 3, 6, 9, that's right here. My x-intercepts are at 10.2 and 1.8. So 1.8 is just a little bit shy of 2 right there. And 10.8, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.2 is just a little bit past 10 right there. Okay. Vertex is at 6, negative 9. So 1, 2, 3, 4, 5, 6. Let's do this the right way. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. Right there. All right. I know I'm getting picky. Let's see. So just doing all of this analysis, I actually got 4 really good points out of all that. I could do more if I wanted to, right? We could easily figure out that since the center is at 6 and this point is at 0, 9, then 6 units in the other direction would be 12 on the x-axis, would have to also be up at 9. 11 and 12. 12 is right here, and it would also have to be up at 9 at that point because it's symmetric. It's a symmetric shape, right? So right here, I would have to be coming down here. I have to go through this point. I've got to turn. Got to come back up through this point and come down through here like this, right? The straighter parts are a bit easier, right? It's the turn part. Knowing exactly where that point is to turn is more difficult. All right, so I hope that really helps you see all of the things that we need to be able to do when you're given the quadratic function equation. All right, here's the next one. The 1/2 x squared minus 6x plus 9. Here's the parabola. First note that the vertex here, the low point in the curve, is at 6, negative 9. The vertex was 6, negative 9 as we calculated. The y-intercept at positive 9. And then the x-intercepts, as you can see, just a little bit less than 2, just a little bit bigger than 10. Let's actually compute those if we can. There they are, 10.24 and 1.76 as we calculated. Let's finish up with 3 more examples, but from a different direction and a different goal. Okay? All dealing with quadratic functions, but with a different aspect of what we need to look at. Here in this one, it's the reverse of what we were just doing. We're given some information and we need to create the equation. So whenever you have a parabola in a graph like this, either they have to give you 3 points on the parabola or a vertex and some other point. And the most common is to already know the vertex because you're maybe designing where you want the curve to be or where you need it to turn at or whatever. Okay? So if you have the vertex, which most of the time you will, and then some other point, you can actually create the equation of the quadratic function itself. Okay? So I'm going to use the vertex form of the equation. Y equals a x minus h squared plus k. I'm using y instead of f of x because I need to actually plug in a y value. Now don't forget, we already know h and k, 5 and 7. So I already know this much. And then I also know that when x is -3, y is -1. So if I take that into consideration and put -3 for x and -1 for y, I've filled in all of the spots except for a. Well, I need to know what a is, so I'm going to solve for a here. -3 minus 5 is -8 squared. I'm going to subtract the 7 from both sides here. That's going to give me -8 is equal to 64a. And if I divide by 64, I get that -1/8 is equal to a. Well, that's great. Now that I know what a is, and I know what h and k are, I can actually write the function here. I can say that this function, f of x, is equal to -1/8 times x minus 5 squared plus 7. And this is the vertex form of that function. The only other thing that you may want to do, it depends on what the question is asking or what your goals are with it. You may want to convert it into generic form, to general form. To do that, we would just FOIL out the x minus 5. So f of x equals -1/8. FOILing out the x minus 5 would give us x squared minus 10x. I don't think I'm going to have enough space, so I'm going to leave out the f of x for a moment. -1/8 x squared minus 10x plus 25 plus 7. I would then distribute the -1/8 here. That would be -1/8 x squared. -1/8 times -10 would be plus 10/8, which is 5/4x. And then that would be -25/8. And I'd want to add the 7 here, right? But to add it with the 25/8, they'd have to have a common denominator of 8. And 7 times 8 is 56. So I'd have 56 minus 25. The other version of the function here is 1/8 x squared plus 5/4 x. Then that would be, 31/8. Okay? So either way, the general form or the vertex form of the equation doesn't matter unless the instructions say, or if your goals for whatever you're modeling matter there. Okay? So you can actually create the equation from information. You just need the vertex and one other point, and you can easily solve for a by just plugging in the vertex and the point. And then once you have a, you can create the function with the a, h, and k. Now, a couple of word problems here. Jim sells an X amount of hot dogs, and when he does sell those X hot dogs at whatever ball game he's at, his profit for those X hot dogs is given by this equation. Okay, so then the question is, what is the maximum that his profit can be, and how many hot dogs specifically should he sell to reach that maximum, right? You don't want to go overselling and you don't want to undersell. We want to know exactly how many hot dogs should he sell, and then call it quits for the day and say, okay, that's how many we make, and then he would maximize his profit. Well, the reason why we can see that there is a maximum, two things. First, x squared, so I know it's a parabola, and negative is my a number here, so I know that it's facing down, which means it does have a maximum. And then you just got to remember, where does that maximum occur at in a parabola? The vertex. So all I need to do is compute the vertex. Okay, so my vertex, let's go ahead and calculate that. Right, vertex h is negative b over 2a. So that'd be 2 times negative 1/50th here. The negatives are going to go away, and I have 10 over 2 times 1 over 50 is 1 over 25. And of course, to divide a fraction, I would flip, which would give me 10 times 25, or 250. So my h is 250, okay? And then, so my k is going to be p of 250. So then I would have negative 1 over 50 times 250 squared plus 10 times 250 minus 250. That's a coincidence, huh? Okay. So then 10 times 250, and then I got 250 squared. That's going to be 2,500. Half of that is 1,250 minus 250. This should be 1,000. Okay, so which one is which? That's the key to this question right here. What is the maximum profit, and how many hot dogs should I sell to obtain this? Well, remember, the hot dogs is represented by X, right? He sells X number of hot dogs, and then the Y value is the P, the profit. Okay, so how many hot dogs should he sell? In my vertex, remember the H is the X component. So he should sell 250 hot dogs, and for doing that, right, the profit at 250 hot dogs, we just calculated that, was $1,000. Okay? So you can easily answer a maximum problem when you know you have a parabola facing downward like that. You just find the vertex, and then you got to distinguish which one is asking for which piece of information. Okay? A football is thrown down the field according to the following approximate model. The height at some time t, h is height, t is time, is computed by negative 16t squared plus 38t plus 6. All right? So what is the maximum height of the ball? I'm sure you're sitting there while you're watching all the football games and wondering, I wonder how high he just threw that football. Probably not. I'm just joking. I don't really watch much football myself, but they do make for interesting problems. Okay? I actually created this problem getting some data from a local quarterback. So I used some of the numbers that they listed to make it. And it's actually pretty accurate. So look, right here, what this is saying is that the original height of the ball when t is 0 is 6. So we're saying about 6 feet off the ground is what it was thrown from. And it started with now remember, this t is not x, right? This is just time. So the height has an initial velocity of 38 feet per second. And then, of course, the pull of gravity at the negative 32 over 2 feet per second. So what is the maximum height of the ball? Again, notice it's t squared, which is going to give me a parabolic shape of my graph, and it's negative, which means there will be a peak. There will be a maximum amount to this. So what is the max height? I'm going to have to find the vertex, right? The vertex in this case is going to have a t value and an h value. Okay, not to be confused with h and k. I know those things go like that. But I'm going to compute the vertex, right? And instead of h and k, I'm going to use vertex sub x like this. That's what we called h before. It's the x component of the vertex. So I'll just do v sub x is negative b over 2 times a, like so. Okay? So that's 38 over 32, which I can reduce a little bit, right? That would give me 19 over 16, which is 1 3/16. So 1.1. Let me go ahead and crunch this just to make sure that I don't get off task here. 19 over 16. Yeah, okay. 1875. That's good. It'll probably be easier to plug in the 19 over 16 though, because remember, for the vertex y component, I'm going to do the function h of, right, because our function name is h this time. Don't confuse that with the h from earlier. This h is just a name of the 19 over 16 here. Okay. So just to speed us up, I'm going to plug that in. That's going to be negative 16 times answer squared plus 38 times answer plus 6. 28.5625. Okie dokie. Now remember, the vertex x in this case is not actually an x, it's actually a t. And vertex y in this case is not actually a y, but a height, right? Because remember, that was our function here. The height was our y value, the t was our x value, but I'm not using x and y here. I'm using height and time. So that means this first thing in the vertex right here is the number of seconds that it took to reach that maximum peak, right? So he throws the ball, and 1 and a little bit, more of a second later, it's reached the peak height. And how high is it? Well, h is measured in feet. It's about 28.5-ish feet off the ground. Okay? Incidentally, if you're interested, I went ahead and carried the calculation further with some other trigonometry and things like that, and this particular pass would end up going 55 yards in about 2.5 seconds. Okay? So I hope that these applications and all the things we talked about earlier has helped you understand quadratic functions better. Stay tuned for synthetic division and polynomial analysis. So one last quick look. There's the 5, 7 point, and there's the -3, -1 point. The point over here at A is supposed to be the vertex. Notice if I type in the equation that we calculated, it is actually the parabola whose vertex is at this peak, and it goes through the point B like it's supposed to. Also, we had the other version of the equation, -1/8 x squared plus 5/4 x plus 31/8, and it as well is the parabola that has the vertex there at A and goes through the point B. Thanks for watching.